All right. Okay, there now. Good morning and welcome back to the lecture. Sorry for a little bit of a delay. Today we want to wrap up the analyzing relational data topic. The focus of this lecture will be on this interview that you have access to on the course website. This interview was done around 10 years ago, more than 10 years ago. It was when Hadoop and MapReduce and other frameworks were at their infancy, like early days. And this is an interview from someone who is an expert in databases. And this is their point of view. And basically, at a high level, they claim MapReduce is garbage for database stuffs. And we want to talk about this. If you're interested, you can read the interview here, but I have a summary of that in my slides. So that would be the last topic we talked about, because here we talked about relational data, right? The idea here is that we want to potentially replace databases in some particular applications. And we learned about how to implement fundamental functionalities such as join in big data frameworks last time. So let's see what this guy is talking about. Are these points valid, or they were a little bit jelly back then because MapReduce was getting a lot of attention? So they say MapReduce is a major step backwards. And the reason is this. They said, the claim is that there were like 40 years of research in relational databases, and MapReduce is basically ignoring the most fundamental aspects of relational databases. For example, the schemas are good, right? When we have in databases, we have a schema. We know that this column has a data type of integer, for example. There are multiple benefits in that. For example, we can check for consistency. So if somebody tries to write string into that field, which is an integer, the database would reject that, saying that this is not compatible with the expected schema, right? And then the separation of the schema from the application is good. When you have a database and you want to figure out how your data looks like, you look at this schema, which is like a catalog of the data that you have. And you know that, for example, we have 5 columns. These are the data types and how we can work with the data. But if I want to do that in your assignments, for example, in 451, there's no database. The data reading schema is there embedded in your code, right? You read text, you tokenize it, and you try to interpret what the data is. There's no schema, so it's in the code. So if I want to improve the code, I have to dig into the code, figure out, okay, how you store, how do you read the data? But in a database, we have the separation of how and what. So we know, okay, we have this data and I don't care how it's stored. It's not the case in MapReduce. And finally, high-level access languages are good. So nobody is advocating writing in assembly these days. Why should we write stuffs in MapReduce, which is the assembly equivalent actually here? And we have looked at this already a little bit. We know that there are other things like Hive these days that try to solve the issue. They didn't have such tools back then. So when you look at these claims, all of them are valid. Right? They're correct. And then MapReduce is poor implementation. Again, a lot of the research has gone into relational databases, like they have indexes, right? And indices are extremely useful for fast lookup. It can improve the lookup speed by 1 or 2 orders of magnitude. In MapReduce, we don't have such fancy stuffs. You want to find something in a file, you read the file. And that thing that you're looking for can be the last word in that file. So it's really slow. And this one is interesting, is that MapReduce is not novel. People who advocate for MapReduce and they're so excited about it, this is like a 20 years old idea, which was also true to some extent. And finally, MapReduce is missing some key features that relational databases have, like bulk loaders, indexing, updates, transactions, right? MapReduce doesn't have any of these things. And obviously, MapReduce is not compatible with relational databases. So we want to look at some of these things. Obviously, over the years, some of these have been improved significantly. And let's see where we are with regard to these things. First, before we look at the solutions, let's quantify what I just said. Let's see, the claim was that MapReduce can be pretty slow compared to relational databases when you want to use it for relational data. In these experiments that I'm presenting here, we are comparing Hadoop with two parallel databases. To be fair, they should be parallel as well. So Vertical and DBMSX are two parallel databases. And here we are looking at the performance of this command, which is basically checking for some statement to be if it's true or not. So it's a selection statement or the equivalent of grep. We want to see if we can find something or not. So here, as you can see, the bar for Hadoop is much taller, which is bad because this is execution time. So lower is better. And here we have two types of experiments. So here in this case, we increase the number of nodes that run Hadoop or the relational database. And here we keep the load per node constant. So it's always like 500 megabytes per node load. So basically, as we increase the number of nodes, we also increase the workload as well. So you expect the runtime to be roughly the same because you increase your resources 10 times, you increase your workload 10 times. So ideally, it should be pretty much stable. It is to some extent. Hadoop goes up a little bit. So so as you can see, these systems beat Hadoop. And then here it's a different type of the experiment. So the workload is the same. So as you increase the number of nodes, you should expect it to finish faster. So from 25 to 50 and 100 nodes, as you expect, the runtime goes down. But across all of these experiments, relational databases beat Hadoop. And you may ask, what is this white line? Because the Hadoop line has like two lines. So the issue with Hadoop is that because it has multiple reducers, when you want to do some calculation here, at the end of the day, you need to combine all of those small files, right? Because they are on different nodes. And that white part is the time we need to concatenate partial results at the end to produce like one file. And they test some other queries. So here, this is selection. So our focus is on this where. So for example, we want the stuffs where PageRank is greater than a threshold. Again, as you can see, these systems beat Hadoop significantly. And aggregation is also interesting because we know that when we have aggregation, Hadoop requires shuffling. So let's see how it performs. Again, as you would, or I don't would not expect, these systems beat Hadoop. The last one is probably the most interesting, join. We learned about this last time and how we can implement it. And relational databases are optimized a lot for this operation because it's a very heavy and common operation. So they make sure that they optimize a lot for join. And the plot is disastrous for Hadoop. We are basically looking at orders of magnitude difference in execution time. So it's terrible. Why was Hadoop so slow? It turns out that a lot of it boils down to string manipulation. And that's because of lack of a schema. Because in Hadoop, everything is text pretty much. And then you interpret it, you need to tokenize it. But relational databases have schemas. So they store stuff in binary format, which is much more efficient for processing and reading and writing. So the key ideas here are binary representations are good. This is something that Hadoop didn't have at the time. It's mostly text files that we process, right? But the issue is that in order to go from a string to a binary representation, you need a schema. You need to know what this thing is. Is this text a string an integer? Is it a string? Is it a float? What is it? I need to know the schema. And the other advantage is that it allows for logical and physical separation. And this allows you to do cool things. So let's look into this. Okay, so we have the logical view and the physical view. What do you mean exactly by these things? This representation that we looked at last time, this is the logical view of our data. This is how we think about the data in our minds. We think, okay, it's like a table, different columns, different rows. Make sense? But you cannot write something like that on a disk, right? In the disk, everything is like an array, a binary array, right? It's a buffer. How we go from such a logical view to a physical representation of data on disk? Let's talk about that a little bit. The first big decision that we have to make here is, okay, if I want to convert this into a binary array to write on disk, am I going to do row or column store? What do you mean by that? Well, you want to store this data and it's two-dimensional. Obviously, you need to make it one-dimensional in order to write it to disk. So one way to go is to write the first row to the disk, and then you move on to the second row, you write that to the disk, and then third row, so on and so forth. So basically, you write all of these rows back to back. This is called row store. Okay? This is typically what we do and what we have seen until now. Does that make sense? Because we are reading records from a file, and it's typically line by line, and every line is an entry, a record, right? Because in a database, every line is a record, for example, information for a particular student. So that's how we were processing the data. That's how the files were written. Okay, but there's another way to store the data. We can also have column store. Instead of storing the first row and then you move on to the second row, how about we store the first column and then, so this is the first column, and then you move on to the second column and the third one, so on and so forth. How about that? So that's another way to do this. Now, let's compare them quickly. The row store, it's easier to modify a record in place update. So this is a particular student's information, like a student ID, a student name, the grade in the big data course, something like that. So every row belongs to a particular student. So if I want to update the information for a particular student, it's easy, right? Because, for example, if I want to do something for this record, I would go here, and this is that student's data. I can modify it easier. But if you want to do the same thing here, the pieces of information are spread across the data that we have. For example, this is here. This information, the ID is, I don't know, is it here or here, for example, and then this guy is here, right? So if I want to update something, I need to basically go to multiple places on the disk to update it, which doesn't have a great performance because of disk seek and all of those operations. The downside of row store is that you may read unnecessary data when processing. Why? In relational databases, many operations update a particular column of data. For example, I want to scale the final grade. I want to add like 2% to all of you. So I want to basically modify, if this is the final grade, so I want to modify this column of data. So if I want to read that or update it, as you can see in the row store, I probably read the whole thing here, because on the disk you cannot read 1 byte, right? You read a block typically. So you read a ton of data around it in order to get access to this thing. And then in order to read this one, you read around that piece of data. So it may read unnecessary data. So the advantage of column store, on the other hand, is that you only read necessary data. So if I go back again, so if I want to update the grades, or I read the grades, I only read or update this part. So all of the data I need is in one place, which gives me much better performance. On the other hand, tuple writes require multiple operations. So if you want to basically update a particular record, so if I want to update the information for a particular student, now the information is basically scattered everywhere in column store. So tuple updates are complex. Okay, so there are trade-offs. But at the end of the day, when we work with relational data that looks like tables, it's typically beneficial to use column store format instead of row store. So it's not always true. It's when we have relational data. There are some advantages that I'm going to list here, and then I will explain them in detail. So this is basically the roadmap for today's lecture. So there are inherent advantages, for example, better compression that I will talk about next, and read efficiency. So read efficiency I talked about a little bit, because you want to read one column of data in column store, all of that data is stored in one place. So maybe by just performing one read operation, you read all of that. So it's much faster. It also works well with some features that relational databases support, such as vectorized execution and compiled queries. So the plan is like this. I'm talking about compression first, and then I move on to explaining what's vectorized execution and what's compiled queries. And then I wrap up this lecture by arguing if we can implement these features in MapReduce. Is there any question? Okay, let's talk about compression. So we have two options, row store and column store. So which one is better for compression? I mentioned that as an advantage, so probably the answer is column store. But my question is, why column store is a better way when you want to compress your data? Or better to say, why column store gives you more opportunities to compress your data as compared to row store? So voice or text? Go ahead. What do you think? Why column store is better for compressing data? Okay, the first answer is this. Since records of the same type are stored right next to each other. Same type of data are together. Yes, that's the reason. If you look at this, it's so messed up. It's, for example, the first one is the student name, so it's a string, and then this one, student ID, is a number, and then this one is a grade, again a number, but it's a different number, right? Very different. That one's a big number, this one's a small number, and then so on and so forth. So look, different types. But when you look at here, like all of these are strings. These are all names. These are all numbers, all your student IDs or all of your grades. So as you can see, the data, the same type, are right next to each other. This is better for compression. Why? Because compression works based on the principle of redundancy. So whenever you have redundancy in your data, there's opportunity for compression. Let me give you an example. I want to send you this data, 1 million ones. So it's 1, 1, 1, 1, a million. If I don't compress it, I have to send you 1 million ones. But as you can see here, there's a ton of redundancy. All of the numbers are exactly the same. So there's huge potential for compression. Instead of sending you a million ones, what can I do? I can tell you, hey, 1 million ones. Or I say, I send you 1, 1, and then I tell you a million of the same thing. This immediately compresses the amount of data that I need to send to you. So it's a lot of opportunity. So if we basically arrange the data like this, where in the column store, where we have the same type right beside each other, that gives us more opportunity for compression. And that's the why. Now, that means we can apply standard things like gzip, right? But you can do some even smarter compression techniques. How? Here's one example. Run length encoding is a simple technique for compression when you have repetition in your data. The example that I gave you, a million ones, is basically run length encoding. What does it mean? So let me explain it here. Look at this array of data. This is, for instance, let's say this is the operating system on cell phones. So I'm keeping data about cell phones, and one column of data is the type of operating system that phone runs. For example, the blue one is Android, right? So all of these are Android, and then this one is iOS, okay, the green one, and then this is one Windows, and then Android again. So this is looking at that column of data, but because of column store, it's flat, right? It's horizontal. So this is all of the data that I have in that column. Here, this is the idea that I told you. Instead of, for example, here, saying Android, 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 we can say Android 3 more times. That saves the space a lot. So we can encode it like this. We can say Android and 3 more times. So basically we have to copy the first one anyways. And then if it repeats, you add the number. So Android 3 times, and then now we switch to iOS. So we write that, and then we have that 2 more times. And then we have this poor Windows guy. And then we switch to Android again, and we say, okay, it happens 1 more time, supposing that the data ends there. So that's the idea. So as you can see, we can compress the data a lot, and we have more opportunity if the cardinality of the set is small. So the cardinality is basically the number of different things that we can have. So here we have Android, iOS, and Windows. So supposing that these are the only 3 types that we can see, the cardinality is 3. It's good because when the cardinality is small, it's more likely that something repeats. Because if I have like 1,000 different things, it's kind of random. But if I have only 2 or 3 different things, then it's very likely that something like this example happens, that we have the same thing back to back, and then we can use run length encoding to compress the data. The best case is Boolean, when you have only 2 things. That's the best case. That's the biggest potential. All right. Any questions about run length encoding? Again, I remind you, we have this opportunity here because of column store. When you represent data like this, and because we have things of the same type, for example, all of the operating systems written in the same row, now we can perform compression techniques like run length encoding. So there are other techniques that we can use as well, depending on the data type that you have. For example, if these are integers, so if these are student numbers, so these are integers, or the final grade, again, can be integer. We know various smart techniques for integers. Run length encoding is applied to anything. It doesn't matter what data type. But if we know it's integer, we can even do much better. If you remember, we talked about all of these integer compression techniques, like vbyte or word align techniques like simple 9 and things like that. So if we know that's integer, we can even improve compression even more. Okay, so that's the idea. And now let's go back to the criticism that the database guy had. Well, all we have seen until now was row store because we really didn't need it. We didn't need column store, but now because we are talking about relational data, column store makes sense. And does Hadoop support column store format? Yes, we have a format called Parquet. And CS451 students will work with this format a little bit in your next assignment. It's pretty easy. I mean, you don't care. There's an interface. You read it from that file. All you need to know is that it's column store. So it's available in Hadoop ecosystem. So if you're working with Hadoop or you're working with Spark, you can use this special format. Okay, just one slide on it. I just wanted you to see this term and be familiar with it a little bit. So Parquet, a column store format that we can use. Now, we talked about better compression. We talked about read efficiency a little bit. Let's move on to fancier features that we have in relational databases. Let's learn them a little bit, and then we circle back to can we implement them in MapReduce. I'm not getting any questions today. Is everyone happy or confused? Okay, let's talk about vectorized execution. You remember this slide, hopefully, from previous sessions. So in Hive, we talked about this. If you have a SQL query like this, we can convert it into MapReduce. And if you remember, we in one of the steps, we came up with this logical plan that helped us to figure out the physical plan. If you think about this, and I will talk more about it, when you want to implement this, when you want to move on to the physical plan, this should somehow involve many loops. Does it make sense? Because we are reading stuff from a file and we apply something. For example, we do selection and projection. This is a simple case. So we read data, and if it matches some conditions, I keep it, otherwise I throw it away. So at the end of the day, when this is compiled, it should be a loop that I go through the data in that file, and if it matches condition, I keep it, otherwise I throw it away. So this involves many loops. Let's talk about loops a little bit. Here's a program I have. Like an integer size, and then I have an array of integer with that size, okay, and then I have a Boolean array with that size. So I have, so let's see, how much is this? So 100 million. So I have 100 million integers in an array, and I also have another array with the same size, but it's Boolean, true or false. So here, a simple program. I'm looking at these numbers in the integer array. If it's positive, I write true to the Boolean array. If it's negative, I write false to that corresponding index. Okay, so I'm creating like something like a map based on the fact that is it positive or not. So that's one way to do it. And here's another way to do it. So let's see what these are. So this one loops through the array, okay, from 0 to size, so from 0 to 100 million. And it looks at so this is the first array. This is the integer array that I have. So it looks at every item. If it's positive, it writes true or false in the corresponding binary array. Very simple. What do we do here? It's again from 0 to size, except that it jumps by 8. The first line is exactly the same. And then in the second line, it also does this calculation for the next row as well. And then it does it for the next row. You can see that the indices are like I plus 2, I plus. So in every iteration of the loop, it processes multiple rows. So in this case, it processes 8 rows of data, okay, or 8 indices into that array, and then it jumps by 8. So process 8, jump by 8, process 8, jump by 8. But here, the difference is that it processes 1, moves or jumps 1, processes next one, moves to the next one. Okay, so that's the difference. In terms of like the logical view of this, they are doing the exact same thing. Because at the end of the day, we need to do 100 million comparisons. Either we do it 1 by 1 or 8 by 8. We have the same number of instructions there. But if you run this, you will see that one will be faster than the other one. Ideas. Which one do you think is faster, right or left? And why? Maybe in the chat, tell me first which one you think is faster, or if they're the same. Which one's faster? Right is faster, right, because of overhead of looping. Yes, so right has more votes. And the reason, as mentioned correctly, is the overhead of the loop. So I was not very accurate when I said both of these have 100 million operations. Yes, both of them have 100 million operations of this type, plus whatever we need to do in the loop. The loop itself has some instructions, right? Because we need to increment a counter. You need to check to see if we have reached the limit for the loop. So these are all instructions. Although we don't care about them that much, they consume CPU cycles. And because here we have to do these comparison and incrementing 100 million times, but here we do these things 100 million divided by 8 times, we have less overhead for the loop in the right solution. Let's test this quickly. If it's right. There you go. So I have two programs here. They're even simpler than my slide example. So what I have here, I have a loop that goes from 0 to 1 billion, and it adds up all of the numbers from 0 to 1 billion. Okay. And let me see if I can open the next one in the same window. My Vim the skills are still okay. All right. So left and right, do you see my code? Do you see the code? Yes. Thanks. So what I have done, I have unrolled the loop. Okay, so instead of doing one addition, I'm doing 10 additions. So when I start, I go from 0 to 9. I add up all of these 10 numbers, and then I move on in the next loop. I go from 10 to 19. So it's the same thing, adding up numbers, but I've unrolled the loop. So that's the terminology for this, unrolling the loop. And at the end, they write what the sum is. Okay. And if I've already compiled this. So when you run it, it takes some time because it's adding up a bunch of numbers. So it's this. So to actually better measure how long it takes to run, in Linux, you can add time in front of whatever you're doing. It will measure how long it takes. So it will be the same thing. It runs and prints output, but it also gives me how much time. So the first one, this real time, is basically the wall clock time. So we spent 3.7 seconds on running this. Now let's run the unrolled version, the one that I calculate 10 at a time. So this one finished in 2.2 seconds. The previous one, 3.7 seconds. That's a huge difference. That's more than 50% increase from here to here. That's crazy, just by unrolling the loop. Make sense? Nothing is free. What's happening when I unroll the loop? So there should be a trade-off when I do that. So we have a question, but is this because the operation inside the loop is very simple? It's part of it, right? Because the operation inside the loop is so simple that it's comparable to the operation of the loop itself. So when you reduce the number of operations in the loop, you see gains. But if, for example, it takes 1 second to complete one iteration, you probably won't notice the overhead that much. That's true. So it magnifies it. But it's also a very important point that I will get to. In practice, many operations are very simple. So that's a very good observation. I think what we lose here might be that the binary of the second one might be a little bit bigger. I'm not sure about that. Let's try. So this is count. And then where's the other one? Sorry, I have so many things here. And then count unroll. Yep, the binary is a little bit bigger. So that's what we lost. Nothing is free. So whenever there's a gain, there's something you lose. But we don't care about those. Is that like 8 bytes? I don't care in most cases. So basically, next time you interview for a job and then you come up with the solution that's like O of n cubed, and they tell you to improve it, you can unroll the loop. Don't do that because they kick you out. That was a joke. All right, so that was interesting. A simple unrolling the loop can improve the efficiency significantly. Going back to what we had, and these are some measurements for this code because it's a little bit different from the example that I ran. So, so that's the idea. Why should we care about this? Why does it matter? If we have a query like this, as I said, when you compile it, when the compiler compiles this, like let's think assembly, right, at the lowest level, in order to implement this where clause, we need a loop somewhere that, okay, loop through all of the items. If page rank is greater than X, keep it. So it has a loop. And this was an interesting thing that was mentioned in the chat that, but yeah, do you see this because the body of the loop is so simple that the overhead is tangible. But in practice, in many cases, the body of the loop is very simple. Like this query, what do we have inside that loop? There's one if. If page rank is greater than X, keep it. So good observation, but it is actually the case in reality. Unfortunately, it's even worse than the simple loop representation that I talked about. In practice, we have chain of operations. So basically, when you implement a query, in order to actually handle that query, it's like constructing a chain where basically we have one loop, and then the output of that loop goes to another loop, and then that goes to another one. So there's a ton of function calls, okay? And then there are also some other function calls for opening a socket and then calling next to get the next row or next item we need to process. And then at the end, we call the close function. So let me explain this in this example. For a very simple query like this, and it will be worse when it's a bigger query, something very simple. We have like a chain of operations like this. First, we have to read the stuffs. These are the page rank stuffs we are reading. And then we have this check, the where clause, the selection. Does it match or not? And then we have the projection operation. Okay, so out of that row, we only care about these columns, these two columns, the page URL and page rank itself. Throw away the rest of them. So this means that, okay, each of them should call open first and then call next to get the rest of the stuffs. And then that will be passed to another one. So there's multi-layer of just calling. So a lot of function call. So what does that mean? It means that the overhead is a lot. Simple operation, a lot of overhead. What you do here, this is just a simple if. What is this? Just throwing away unwanted columns, right? The operation is so simple in every stage, but there are many of them, and we have all of these function calls. So there's a ton of overhead. So the message that you have to get here is that, okay, if there are many rows of data I need to process, this one by one processing is a very inefficient way to implement the stuffs. Hopefully everything makes sense. We now learned about loop and why the overhead causes problems, and also we have something like this. Okay, one by one processing has a lot of overhead because of the loop, because of repeated function calls and all of that. So the solution is basically not to use that version, but rather use something like that. It's not exactly like unrolling the loop, but in essence, it's the same idea, and it's called vectorized execution. This is a well-known feature in relational databases. Fancy name, but really what it does, instead of processing one record at a time, it processes multiple rows of data at a time. Okay? So that next function that we just talked about, instead of just returning one row of data, it returns a vector of tuples. It returns like 100 lines. In practice, it's something like 1,000 lines at a time. And then you have to rewrite your operations. So instead of working on one row, now they should be able to handle a vector of rows or items. Okay, before I move on, is there any question about vectorized execution? Fancy name? pretty simple idea available in relational databases. What I will talk more about soon is, can we have something like this in MapReduce, because it's a nice idea. But before I talk about that, let me talk about compiled queries, which is another interesting concept in relational database. So we have a query, and we have these kind of logical plans, and we come up with the physical representation or the execution plan. And at the end of the day, everything is compiled, right? Yes, when you run SQL, at the end of the day, it's like C or C++. And that compiles the stuff to machine code, right? CPUs only understand assembly, correct? So it doesn't matter how fancy your programming language is, at the end of the day, it should be assembly for the CPU. So when you run a query like that, it will be something like this. Now, and coming up with this thing that you see on this slide is time consuming. And you know about this a little bit now. We need logical plan. We need to come up with multiple physical plans. We need to optimize and find the best plan, things like that. So every time you issue a query, the system has to go through all of these steps in order to generate some code that can be executed on a CPU. It's a pretty long and difficult path. In some cases, a particular query is repeated many, many times. Sometimes like once a second, maybe. It's an essential query in a system. Or it's a query that's issued by many users in a system. So we expect a lot of that query. And if you want to do just a regular way of handling it, every time that query is issued, you have to go through all of these steps to get to the compiled code, which takes time and really limits the performance of your system. The idea is pretty interesting. The idea here is, hey, for some stuffs that we do a lot, how about we keep the compiled version of it instead of starting from scratch? So that's a high-level idea. So this way we avoid creating the machine code every time. There are queries in system, for example, on Amazon, that is executed a lot. Like every user does this, for example, when they add something to a cart or they browse an item, something like that. We can keep the compiled version. Obviously, sometimes that function has different inputs, right? It's not like the static SQL query, but the input changes. For example, it's a query that basically gives me total sales over a period of time. And then that period of time is the input to that function. So it's not like a static thing. It needs some parameters. That's fine. So we compile it, and then we also pass parameters or arguments to that query as well, in case that query requires some inputs. For example, the time, the date, which user, things like that. These parameters will be passed because it's assembly and you can do that, right? So you can pass references to that function. So that's the idea here, that we compile and we keep the compiled version and we use that. All right. So coming back to this big picture, let's see what we have done. So we talked about vectorized execution, and we just talked about compiled queries. And now we want to know, can we have something like that in MapReduce? Okay, why not Hadoop? Why we don't see it? Well, the answer is no reason why not. So back then, Hadoop and big data area was pretty young, and they didn't have all of these tools that databases had, right? People looked at databases for like 40 years, but Hadoop had only a few years back then. So it didn't have all of these fancy things. But there's also no reason why not. So we can add these kind of functionalities to Hadoop. For example, we said, okay, we want column store. Can we do that? Yes. Yes. There are actually, again, very high level. Each of these is like a paper, so you can read them to know them in more detail. But the idea is right now, when you work with Hadoop or Spark, the way you think about the data is like this. You process the first row, and then you read the next row, so on and so forth, right? We said if you have column store, it's nice because we have all of those features. The locality of data and all of that, efficiency. Can we have it? Yes. So we have something called RC file, which is basically rearranges the data for you inside an HDFS block. So it groups a bunch of rows. I think the default is 1024, a bunch of rows, and represent them in column format, in column store format. So here, as you can see, this is the first column, right? So this block will be stored like this. So the first row is the first column in that region of the data. So every block is stored in column format. Make sense? So we can take advantage of some of those good things that column store has. Now, moving on to those fancier features such as vectorized execution, that was interesting. Can we have something like that in Hadoop? Well, specifically, let's talk about Hive, because that was the specialized extension of Hadoop to support relational data. Let's see if Hive can support vectorized execution. Yes, and that's a matter of setting a parameter in Hive. So if you set this parameter, it enables vectorized execution. So it's pretty easy to do, and it is supported by Hive today. So I'm going to show you a little bit of code. You don't need to understand it in detail. The high-level idea that you have to make sure you understand is that now all operations are on vectors instead of individual records. Okay, so we have this concept or class of vectorized row batch, like what I showed in the previous slide, that it has an array inside it. And then when you want to do some calculations, when you have some functions to apply on the data, those should support vectorized execution. So as you can see, just want to point out some stuffs here. So these are the changes that we had to make to make this particular code suitable for vectorized execution. So we no longer process one thing, but rather an array or a vector. So we need a loop inside this function to process all of the items inside that vector. Makes sense? So as you can see, we got this selected array, and we loop through it, and we process something depending on what that function is. But that's a high-level idea. So what you need to remember from this slide is that vectorized execution is supported by Hive, which is really cool. How about compiled queries? Can we do that? So we have a query like this, for instance, in Spark SQL. There are multiple ways. So basically, one way is to compile the stuffs every time, or which is slow, or we can basically, if we have a query, we can basically feed the AST tree. If you remember, I talked about AST. So AST tree was the data structure for compiling stuff. So you can basically feed the AST tree into Scala compiler to get some bytecode. And that will be the compiled version of that query that will be much faster to run. And this is a functionality that Spark SQL actually supports. It probably needs more work from your side. So it's not just enabling one flag, but it's a possibility. Okay, so this is now supported in Spark. So the message is, okay, back then in 2009, Hadoop and MapReduce was a very young idea. Especially, it was not optimized for particular applications such as relational data. Over the years, people realized that there's a ton of potential in these new big data frameworks, and they created specialized extensions or libraries to existing systems such as Hive and Spark SQL that provided extensions to Hadoop and SQL to support relational data much faster. Okay, so going back to the key ideas that we talked about, in theory, we can have all of these things in Hadoop if we want to. And over the years, some of these ideas have been implemented for particular applications to make them more suitable for specific needs in some domains. So what mentioned back then, it's now more than 10 years from this interview, all of these are valid points, and we have achieved some of these things because it's not like, no, we don't care about what people learned in relational databases. No, some of those things are really valuable and people paid attention to them and they improve big data systems based on those findings. And that concludes our analyzing relational data topic. Is there any questions? Janya, go ahead.
Hi, Professor. I just have a question regarding the vectorized operation. So the reason we have vectorized operation is to reduce the overhead for loops, but we can see from the example that we are still using loops to calculate scalar additions for each vector element. So I'm a little bit confused. How does that contribute to the objective of reducing loops?
Okay, this is a great point. So the point is, I argued that we want to get rid of these loops, right? Well, we wanted to get rid of basically processing one by one. So that was the idea. But now in my examples, when we try to implement vectorized execution, we saw that in Hive, we have loops inside the function to handle a vector of data. How is this any better than what we had before? So you need to combine all of these ideas that we talked about to understand what's happening. Okay, if you remember, we said that we have a chain of operations. So if we don't have vectorized execution, the first element in that chain reads the first row of data, processes the data, and then passes it to the next stage, to the next element in the chain. And that element processes the data and it passes it to the next element. Makes sense? As I said, there are a ton of function calls there. The way we got rid of that overhead was by processing a bunch of rows at a time and then passing all of those rows to the next stage. So the idea is that in addition to those smaller loops, there are some outer loops or bigger loops that's handling the whole process of data going through the system. So we are trying to optimize that one. Okay, so my unrolling example was just a simple example to make the point of having overheads, and we have to be careful about overheads. And the overhead that we have there is mostly function calls, which is a chain of function calls. This one calls the next one calls the next one, and that was for a very basic query. If we have a much complicated query, that chain could have like 10 stages, for example. And now by processing 1,000 rows at a time, we significantly reduce the number of function calls. So basically, we reduce it by a factor of 1,000. Instead of calling the next stage 1,000 times, hey, here's the next element. Hey, here's the next element. We instead say, hey, here's the next 1,000 elements. So we significantly reduce the overhead there. Let me stop recording. Thank you, everyone. Feel free to leave.